Welcome. I'm Peter Allen. I'm the director of Google University, and I'd like to welcome you. Can't hear. Is this helpful? Okay, great. Thanks for letting me know. I'm the director of Google University, and I'd like to welcome you to one of the very first G2G classes, Googlers Teaching Googlers. It's a series we're piloting this quarter, and we're very excited about the fact that Steve is teaching this class and the fact that you're here. Just wanted to take 5 seconds for a few administrative details. One is there's a sign-up sheet going around. If you would be kind enough to check your name off or add your name if it's not there, that would be helpful to us. Another is that we will send around internet-based, web-based evaluation at the end of the course. That would be also helpful in terms of keeping track. And lastly, just to encourage you guys to think about teaching a course yourselves. We instigated this series because we believe there's a wealth of knowledge inside the Google population and a great desire for learning. And so we have an email alias. It's g2g_proposals. And we'll be sending out more requests, but I just thought since we were here in person, we'd ask you to think ahead. So without any further ado, welcome to Theory and Practice of Cryptography and Steve Weiss.
Hi, everybody. My name is Steve Weiss, and I'm glad to see all these people out here for this class. I'm really excited to teach it, and I think it'll be really interesting and a lot of fun. This lecture today is going to be not as technically oriented. It'll be a little bit of historical and kind of just give you an overview of some of the modern cryptography primitives and constructions. So some of you, this may be review. Some of it, if you're not an engineer, it might be new material. So if you're following on the VC or watching this on video, all the course material is going to be at this website, go/cryptocourse. There's a Presently link right now, so you can follow along with the slides if you're watching live. And all the course material will be posted here throughout the rest of the course. There's a first exercise set that's up, and some of you have already started on that. This is pretty hands-on. There's a couple parts that I'll talk about in the middle of the lecture, and it should be fun, and you're encouraged to work with others on it. There's no deadline. You're not turning it in, and that's kind of the theme for the whole course is come to lectures you're interested in, do the assignments that interest you, and feel free to ask questions. There's also a QDB link on this page, and Presently's got this little chat window if you want to join in. There's some people in there already, so feel free to add a QDB question or whatever you like as we go through the lecture. So, as I said, this lecture is going to be more historical, kind of general. Next week will be more engineering oriented. I'll actually talk about using crypto at Google, and if you're writing code, what kind of things to avoid, what kind of things to do. So that'll be definitely more engineering oriented. So you're welcome to that if whether you're an engineer or not. Third week, I'm going to focus on more theoretical cryptography and talk about some more of the math and the underlying definitional stuff. So that'll be interesting if you're interested in more of the math side or the kind of the theory of computation side. And the last week is going to be a special topic, and I'm going to let you chime in on what kind of things you're interested in. So if you go to the QDB page for the final week, which is also on the main course page, you can submit some topic ideas and vote on them. And I put a few up there myself, but feel free to add anything you're interested in, and we could do a lecture on that. Depending what it is, I might have a guest lecture that week. So that one will be a good general lecture that people should be interested in. So, getting started, like what is cryptography? And kind of the classical definition is that the roots of the word are secret writing. And historically, this has been just keeping messages secret. So it's a military type thing where you want to send messages out to the field and don't want your adversaries to intercept them and know what's going on. And that's kind of the classic informal definition of encryption, is taking a message and rendering it unreadable to somebody who doesn't share a secret. Now, a kind of related thing is steganography, and that comes up a lot in popular media, and you'll see it a lot, and I'll kind of distinguish that later in the lecture. That's kind of hiding messages in plain sight. So I'll give a few examples of that later in the talk. So one of the earliest kind of known ciphers that have come up in history is called a scritali. And this is basically just a stick that you wrap either a piece of paper, or in this picture it's a piece of leather around it, and write your message on it across the different wraps. And if you think about this, the only secret in the system is the size of the stick. So if you get one of these messages with just a piece of leather, a piece of paper, just try a bunch of stick sizes. And that's kind of the secret key that's shared, is if you and I want to communicate a message with a cipher, the secret key is a stick size. So it's not too hard to break, and it's obviously very primitive. But this is called a transposition cipher. So you're basically taking these letters or characters and just reordering. You're not substituting anything. It's just kind of the jumble that's in the newspaper every week, just words that are scrambled up. So a little bit more advanced is called a Caesar cipher. And this is just a substitution. So basically, you take a letter, and then you replace it with a letter that's 3 letters forward in the alphabet. And this is also, ROT 13 is the same thing. It's just a simple substitution. And if you think about this, the key here is just how many letters you're shifting over. In this case, it's the value 3. It could be -3, it could be 26. And this will have a little bit to do with one of the assignments on the exercises that you'll get to do. So this is a very classic cipher that comes up a lot. It's very simple, and obviously knowing the key is very trivial to kind of brute force through. Now a little bit more, this is another example of a cipher. So back in the 70s, there was a Zodiac killer in the Bay Area, and he would send in these messages to the newspaper, like the San Francisco Chronicle, and he'd have these ciphers in there. And this was one of the earlier ones that it was unbroken for a while, and some amateur up in Marin just started, pen and paper, trying to guess what the symbols were. And so what he's done is actually taken a little more complex. He's taken each alphabet letter and has multiple symbols that it could be. So like the letter E might have 5 different symbols, and you can use them each interchangeably. So he's actually kind of smart with it. Is he took the most common English letters like E, I, T, O, N, which appear much more than other letters like Q and Z, and he gave them more symbols. So if you look at the statistical analysis of this, these symbols don't appear as much. So as I said, this one's been cracked, and you can read about it online. There's still some out there that haven't been cracked. So if you want to go play around with some ciphers, this is out there, and it's been kind of sitting there for 20 years now. And so there's more complex ones. So after they broke this, he went back and did something else. And I imagine that some government agency is probably able to break this, but no one's really bothered. But anyway, it's out there, and it's something you can look up. This Zodiac cipher. So a little bit more complicated than that is called, I'm going to butcher the French name, but it's a polyalphabetic cipher. So the idea here is that your key is still basically just doing a substitution, but you're doing a different substitution for each one. So in this example here, the key is Google, and the plain text is by YouTube. That's our secret that we're transmitting. And so the first character you're going to shift down by G. So in this case, you go either to the row or column that's B and go to the corresponding row or column that's G. And the letter that's there is going to be H. And if you keep doing this and you get to the end of your key, what's going to happen is you're just going to reuse your key. So if you're going to say Google, Google, Google is your key, do that across your whole message. And so this is about from the 19th century in France, and somebody published this, and there's different variations on this where you might have different amounts of shifts in the table, but it's basically this idea that you're shifting, and it's kind of depending on the position of where you are in your cipher, and it's kind of just going back and forth. And this has come up in practice too, and I'll talk about that in a minute. So, as I said, this idea of this polyalphabetic cipher was used in mechanical crypto systems as well. So this is a very famous encryption machine called the Enigma, and it was from World War II, and it's been in a lot of movies and books and things like that talking about this. And what it is this machine you're looking at. It's got this keyboard, and it's just a regular keyboard, and these rotors. And basically the configuration of these rotors is your secret key. So what's going on in this picture is that somebody's typed in the letter A, and these rotors are spinning around. And the signal of that A, it's an electric signal, is going to go through in these different configurations, and it's going to come out and output a G. And so that's just kind of the same idea as this table. It's, you've got a key that's in a certain state, and before it was the position of Google that you're in, and now it's the position of these rotors. But that's going to change as this goes through. And so if you notice, the rightmost rotor has advanced positions. So if you see the 2 wires on the bottom are now shifted down one, the bottom wire has gone to the top. And now when you hit the same letter A again, a different letter comes out. And at its core, this is the same thing as that previous polyalphabetic cipher. And the keys here were, they had a bunch of different rotors that you could substitute in. So there'd be many different configurations, and people would plug in these different rotors. So both with this and kind of the previous pen and paper ciphers, the way that people would break these is that even with this complexity here, the underlying kind of patterns and information in the message would still be visible. People could do analysis of what the message looks like. So this is part of one of the exercises on the thing I've posted, is that you're going to actually break a message by doing a little statistical analysis and trying to figure out what it is, because you know that the message is English. And so with this particular example, what they would do in World War II would, these German submarines would have this, and they'd surface and give their weather report every day. And so in the North Atlantic, the weather doesn't change much. So pretty much every day, this submarine would surface, and they would say, it's cold and gray outside. And that's pretty much the weather report every single day. So every day, they knew essentially what was going into this cipher. They would know, okay, well, this person's encrypting, it's cold and gray out every single day. And sometimes to do this, they would also go out and create an event. They would go have a plane fly over, and then 10 minutes later, you'd have this like encrypted radio signal that would say something, and they would know that the word plane is in there. And from that, they could try to determine what rotors had actually generated that message. And this is something that Alan Turing was involved in, and it led to a lot of the development of modern computing, was that, by the end of the war, they had built a machine that would be able to crack the daily key by generating enough of this known plain text. And so this kind of, is how you would actually break keys in the past, and it's still kind of a big part of cryptanalysis, is knowing what to look for, knowing kind of looking for patterns in there, and trying to actually, maybe give somebody some plain text that they're going to encrypt and get them to encrypt something that what they're doing. So kind of a side topic I wanted to mention, because it comes up a lot in internet, people always talk about it, and there's a lot of things, is steganography. So kind of classically, this is the idea that you're hiding a message in plain sight. And so a classic one is this Herodotus. And he had a slave, and what he'd do is shave his head and tattoo the message on there, and the hair would grow back, and then he'd send the slave with the message. So the message is just there, but you have to know where to look for it. And they'd also do this thing where they would take a tablet and carve in a message in the wood and then put some wax on top of it. It would just look like a wax tablet, but if you knew what you're looking for, you'd melt off the wax. And so, this isn't really something that's been done a lot, but it has come up in kind of history. And so some things like invisible ink and microdots. Microdots, what they are is basically, it's a message that's been shrunken down to a very tiny dot. So I'd send you a letter, and the period at the end of the message would be this incredibly small, like microfilm picture. And then when you got the letter, you would just magnify that up, and then it'd be, microfiche in there. And that was used in World War II. People would send letters with microdots in them. Another one here, I've got the finger. So this is kind of stretching it a little bit, but there was a case when there were some POWs in the Korean War, and they took them out, and the North Koreans took a picture of them, as the prisoners, and the guys just flipped the bird in the camera. And the North Koreans didn't know what that was, but it was kind of like, a message back. If you know what you're looking for, if you know what that means, it's a signal to the U.S. that you're doing fine or something like that. And prison gangs use steganography a lot. So they'll have letters that are censored and read through, and they'll do things with the letters that are actually, different fonts or different size or different kernings. They're pretty basic, and prison guards know about this stuff, but people are actually doing this in practice. And one that always comes up, it's in movies all the time, and people, there's slashed articles about it, are low order bits and images. So you take an image, you tweak the low order bits, and the message, if you look at the image and the message in there, because you're just changing a little minute part of the actual image, but you could hide messages in plain sight that way. So people have done research where they've gone out and looked at a bunch of images and looked at the low order bits, and nobody really found anything because it's probably easier to just send an encrypted message directly. And so this is kind of orthogonal to cryptography as well. You can put an encrypted message in a steganographic message. And the reason people might want to do that is if you live in a country where cryptography is illegal, which is still a lot of places. You can't, send out encrypted messages from China, as far as I know, or Saudi Arabia. So there's a lot of countries where you may want to do this. And anyway, so that's a little bit of a side note. And if you notice, maybe there's a message in this slide or something, so you can look at it later. So another thing that comes up, kind of related, are codes. So codes are a little bit different than ciphers, is that the idea is that you're going to have a code book of words that are symbols or sentences that are predetermined. And rather than replace individual symbols, you're replacing like strings of symbols. And so the line is a little bit blurred because they're very similar. But examples of codes might be like Paul Revere, like 1 if by sea, 2 if by lands. Like you've got these predetermined messages, and like 1 if by sea means the British are invading by sea, and 2 if by land means like British are invading by land. And so you've established this kind of code book ahead of time, and you have to know the entire contents of the code book to do this message. And if the British did something that wasn't in the code book, you don't have any way to convey that. So other examples are a Beale code. And this was something back in the 19th century where this guy Beale released a pamphlet that had, it said it was like a map to gold or something. And what he would do is take a book, an actual, book or a source material, and the code would basically say, go to page 55 and then take like the 30th word. So the message was just, 55, 30, and then like 120, 40, and so on and so on. So one of those messages was actually decoded because it was the Declaration of Independence. So that was one, and that was like the first part of the message, and then the rest of the Beale codes, I think maybe one more has been decrypted, but there's a couple more that haven't. And there's a lot of speculation on it, if it's a hoax or if there's any gold. And people have looked at it, and there's anachronisms because like the version of the Declaration of Independence he used was some weird misprinting, so it kind of said, oh, this is actually after it was supposed to be published. So that's kind of a code too, because to do this you need to actually have the same copy of the book to decode the message. Now another one, I'm going to actually play a little audio here. Oops. And this is called a number station. And so basically, during the Cold War and currently, there'd be these radio stations that would just read out numbers all the time or at pre-designated times. And I'll try to play one now. So this is just a, turn it down, turn it back on. This is a German voice reading out numbers or letters. I don't speak German, but there's all sorts of these stations. They're all over the world, and there's still some in existence if you're a shortwave radio operator. And the non-intelligence community doesn't really know what they are, but there's a link to one of them here. You can find more on that page. But speculation is that these are kind of pre-designated codes that the agents would have, saying, if they say 2, 3, 4, 5, then go assassinate so and so. The other speculation is they might be one-time pad encrypted things. I'm going to talk about that in the next slide. And so the last bullet point here is called ECB mode, and I'm going to talk more about that next week, but that means electronic codebook mode. And that's a cipher mode that I'll talk about more in the more technical talk next week. So I mentioned one-time pads, and I want to mention this principle about crypto systems. And it's Kirchhoff's principle, and it's called Shannon's maxim. And basically, the security of any crypto system should only depend on a secret key. Shouldn't depend on secrecy of the actual crypto system, of how it works. So if you think about steganography or codes, all that relies on actually knowing not where to look or not knowing that this is the code book. I mean, you could consider the whole code book to be a big secret, but kind of the defining thing is that I could publish this algorithm or say, hey, this is how I'm going to do my encryption, but I'm going to keep the key secret. And the key is just the core of the security in the system. So the kind of the more way to say this is like, don't rely on obscurity for your security. So publish your algorithms, and basically the only thing that should have any excuse me, the only thing that security should rely on is a small secret key. And this kind of brings us to one-time pads. So the idea with a one-time pad is that this actually comes from the idea that you had a physical pad of paper. And going back to those number stations, this might be that somebody goes into a country and they've got this pad of paper, and there's a bunch of letters or values on there that are completely random. And when they hear this message, they just add the message with the values on the paper and decrypt it. So this is like, in binary, this would be an XOR, but on the assignment, on the exercise, this is going to be adding letters together. So the idea here is that if your key is actually random and has been shared securely, this is called information theoretically secure. So there's no computation that could break this. And the idea is that if I have a message that's a coin, if I have a bit and I have a secret key that we shared, and I say heads is the key plus the coin, the key could be, it's 50-50, that could be heads or tails. So there's no information that can be determined by actually listening to this, as long as the keys are secure. So if this is information theoretically secure, why isn't crypto just solved? Why don't we just do one-time pads and be done with it? Now the problem here is that you have to transmit a large secret message in order to transmit a large secret message. So how do you actually get these one-time pads out to people in the world to start with? If you do it ahead of time, maybe you can do this a year in advance and have a stack of pads that you're going to use, but it's a major problem of doing this. And another thing is that you actually have to do this per message. So, I have to do this for everyone I talk to, for every message I send. I can't reuse these pads. And the second exercise shows what happens when you reuse this pad. So if you do that, you can actually break a message because somebody reused a one-time pad. And another problem is that these keys are as big as the messages. So your communication is now doubled in size. Rather than us sharing a very short cipher secret or secret key, we have to share these huge one-time pads and keep them secure. So where do I keep these secure messages if I'm some spy who's behind enemy lines? So one-time pads are, what is this? Unexpensive. Continue. One-time pads are information theoretically secure, but more or less unusable in practice. I mean, there may be some applications where it could make sense, but in general practice, they aren't secure. And so this is kind of one pitfall that a lot of kind of amateurs on the internet will fall into. They'll say, oh, it's encrypted with a one-time pad, it's secure, and blah, blah, blah. But there's a lot of things to think about with key distribution. So we've talked about a lot of the classical crypto, and what are some of the problems with this? So going back to those mechanical ciphers and the Zodiac cipher and all this stuff, one big problem is these are just weak. These were mechanical systems, they're pen and paper systems, and now with the advent of modern computation, these are very weak and easy to break. So the Enigma machine, that was broken by kind of a modern computer, and these are just not going to withstand modern computing power. Another problem is that these are pretty informal. In the past, there was no real formal way of saying what it means to be secure and what is a cipher and what is a signature and what are these things. And that's kind of a recent development in cryptography, recent being the last 25, 30 years. And I'll talk more about that in the third lecture, about some of the actual formal definitions and security definitions and what it means to actually be secure. And being able to base your security on some problem. I'll talk a little bit about that today. Another issue in the classic is that the knowledge and the technology was very closed. It was available to militaries and intelligence agencies and maybe large companies like IBMs of the world, and it was not available like the average citizen. If you wanted to communicate securely to your friend, not have your government listen, you didn't really have any options. I mean, you could try one of these pen and paper schemes, but they've got all the resources, they've got the knowledge, they've got the resources to actually break a lot of this cryptography. So finally, a big problem if you think about the one-time key is key distribution. If you think about the number of people in the system, even if we had a cipher where we shared a secret key, there's n people and everyone wants to communicate to everybody. That's n squared keys that have to be distributed. And you still have this problem of how do you actually get the key from me to you? If maybe an insecure channel all the time, how do I actually ever get my secret key to somebody else? And especially in a networked setting where I may never meet this person, I may have no means of communication, and how do I actually get my keys out to people? So some things that kind of bring us into the modern era. One of them is standardization of strong cryptographic primitives. There's actually, in modern times, we've got standards that have been kind of vetted and that people have actually looked at and have been subject to public scrutiny. These are publicly available. And it's kind of this Kirchhoff's principle again, is that everyone knows what these standards are. Everyone can look at them, everyone can attack them, and there's no secret about what people are doing. All the secrecy comes back to these keys. Another big development that kind of leads to this modern era is public key cryptography. And I'll explain what that is in a couple slides. And as I said before, third thing is formalization of security definitions, actually saying what is secure, what is a crypto system, and growth. Another thing that kind of brings us in this modern era is the growth of personal computers and the internet. In the past, there was really no way for an average person to do any of these ciphers. I mean, pretty much everything was pen and paper. Maybe if you're smart, you could build some rotor machine yourself, but this technology wasn't really even available to an average person, or maybe even small businesses or typical people. But now almost everybody's using crypto every day, even if you know it or not. And finally, kind of something that also brings into this modern era is more recent, just the liberalization of laws. I mean, for a long time, crypto was illegal for regular people in a lot of countries. And it was illegal to export in this country until recently, unless it was a weakened form. So I think that this is one of the major developments as well, is that governments have kind of relaxed and realized that it's good for people to be open about this and have open protocols and open standards. So I mentioned standardization. I'm going to talk about this for one slide so you kind of know what's out there. And one of the big developments was the data encryption standard. So this is a cipher, just like the kind of previous ones we're talking about, but it's strong. It's something that's been designed to be computed on modern computers and be resistant to modern computers. And it was originally designed by IBM. So the NSA kind of went out and solicited people to design ciphers, and IBM came up with this one called Lucifer. And the NSA went and tweaked with it a bit and then gave it back and said, okay, this is DES. And so people were very suspicious about this. They thought that maybe the NSA put in a backdoor, or that they did something to it to weaken it. And one thing they did actually do was shorten the key length, and they said, oh, don't worry about it, it's fine. So people were very concerned about this. And it turns out that about 15 years later, in 1990, some researchers discovered this technique for cryptanalysis called differential cryptanalysis. And then they realized, looking back, that the original Lucifer was vulnerable to this, and DES was not, or not as much. So basically, the NSA knew about things 15 years prior to kind of public academia doing it, and that's why they changed some of the things about it. So DES was 1970s technology, and by 1999, DES can be cracked in about a day for $100,000. So now that it's 2007, and we've had computing power become exponentially better, DES can probably be broken much faster for much less. Now there's a variant called triple DES, which is basically doing DES 3 times, and you effectively get a double the key size. And this is still used quite a bit, and it's still out there, but people are generally trying to move away from it. And the new standard they're moving to is called AES, and this is kind of the modern era to DES, and it was designed in a more public fashion. Basically, they had a contest where a bunch of different researchers submitted designs, and then they kind of went through a couple of rounds and got comments on it and went back and forth. And the end result was actually developed by some European researchers, and that's currently what is now the government crypto standard. And it's out there, and it's in large key sizes, 128-bit up to 256 or bigger key sizes. So I'm not really going to talk anymore about particular standards today. I just kind of want to give everyone an idea of what's out there. And before I move on, does anyone have any questions? I'm just going to look at the chat on here if anyone has any questions online. No, okay. So let's go back to this key distribution problem. If I want to communicate to somebody, how do we actually agree on a key? If I'm in one side of the world and somebody else is on the other side, how do I get a key to them in the first place? And what happens if either party's compromised? If I'm talking to somebody that maybe I mailed it by mail, and we've got a shared key that maybe it's a DES key or AES key. If one of us gets compromised, then both of our communication is compromised in both directions. Anything that gets going back and forth. And sorry about this. And finally, I said this before, is what happens when a third person wants to join this? Well, now each of us need to establish our own key with her, and when we get n people in there, we have to have n squared keys in the system, and I need to maintain all these keys for each of these people, and it kind of grows quadratically. Every person who joins the system, you need to create a whole new set of keys for everyone else in the system. So in the 70s, a pair of researchers named Diffie and Hellman, and kind of stuff in yellow, it can't really show up as yellow, but the formulas and stuff, that's kind of there for if you're interested in it. There's a couple of researchers who came up with this idea called Diffie-Hellman key exchange. And I've also got this guy Ralph Merkle on there and Williamson. So this is, again, a technique that was invented in the intelligence community by this guy Williamson a couple of years before it was published in academia. So they had the idea this is actually in British intelligence, and it's possible it was invented independently in the US as well. But basically, this is a protocol that you can share a secret with a stranger. I'm going to go into a little bit of the math and not go too deeply into it today, but basically, Alice is going to pick a group, and this is a mathematical group, and a generator G, which is just a value in this group, and some random value X. And she's going to send Bob basically G raised to the exponent X. And this is within a group, so if you've kind of got some familiarity with modular math and things like that, you can think of it mod prime. But we don't need to go into too many details, but she sends this value G to the X to Bob. And I've got the notation broken here, but he's going to do the same thing and pick his own exponent Y and send it back to Alice. So Bob has her capital A value, Alice has his capital B value, and they raise each of these values to their own exponent that they picked. So in Alice's case, she's raising it to X, Bob's raising it to Y. And they end up at the same value, G raised to the X and Y, X times Y. And an eavesdropper, if you think about who's listening on this channel, they see four values. They see the group in the generator, which is basically just some numbers, or the group is a description of a particular group and some numbers, and A and B, which are these G's to the X and G to the Y. And the question here is, how hard is it for it to actually compute the shared value that they have, G to the X, Y? And this turns out to be, to our knowledge right now, is a hard problem. We don't know how to do this effectively. And it's called actually the computational Diffie-Hellman problem. And as of now, we don't have efficient ways to do this. And so somebody listening in on this conversation isn't able to actually determine the same shared secret as Alice and Bob. So they know they share this value, G to the X, Y, that no one else shares. And they can use that to determine a DES key or AES key or any other sort of shared secret. Now, does anyone see any problems with this if Eve is not just an eavesdropper? Yeah, there's a man-in-the-middle attack. And so what somebody could do on this is actually sit on the channel and pretend like they're Bob to Alice and that they're Alice to Bob, and just take their values and then forward a different value, and they're going to know the shared secret that each person is using. So this is a responsive script. This doesn't really solve the problem completely. You still would need to establish n-squared keys for n people. So you'd have to do this protocol with everybody, and maybe you do it for every communication session, but it's not like you can have one key that everyone in the world can use. This was invented in the 70s, and at that time, computation over these large groups can be expensive. And it still is relatively expensive today. It's not especially cheap to do this all the time. And finally, as somebody mentioned, it's vulnerable to a man-in-the-middle attack. This is not, if it's like a wartime scenario, or if you have somebody active on the line, they can sit in the middle of the line and switch messages out and are actually able to completely break this protocol. Now, since then, there have been new protocols developed that are resistant to man-in-the-middle attack, and there's more modern options out there. But this is kind of innovative because it's the first time that two complete strangers can actually establish a key where somebody eavesdropping in the middle can't determine that key. The other interesting thing is that this is based on a hard mathematical problem. It actually has some basis saying that if you can't solve this hard problem, you can't break this protocol. Versus some other scheme out there where, this is kind of the first time that you actually have some sort of mathematical reason why this would be secure. And if tomorrow somebody figures out how to solve the, discrete log problem or computational Diffie-Hellman, this will break. But that's a hard problem that people have been looking at for a while. So you've got some confidence that it's actually going to remain hard. If you're interested in this, the original paper is on the wiki page. You can look at it. It's a fairly easy read since this is one of the first kind of papers in the field. And if you're interested in that, you can read through that. So we've still got this key problem. So what if you could have a single key that's public, that anyone in the world could see, and they could use it to encrypt messages to you, but not decrypt your messages? So the idea here is like everyone in the world might have a post box out there that you can drop letters in, but no one else can open the back of the post box unless they have the private key. So anybody can send to anybody, but only you can open your own box. So this, this crypto system would consist of three algorithms, G, E, and D. And so the first thing Alice would do would be to generate what's called a key pair. And so this, hypothetical public key and a secret key. And she would publish her public key. She could put it up on her web page, in a phone book, She could, call somebody over the phone and tell them what their public key is. So now what Bob can do is just take that public key and encrypt a message. So anybody can use this public key. There's nothing secret about it. You can put it up on a billboard, doesn't matter. And he can, generate the ciphertext C. So then he can send the ciphertext to Alice, and only she can decrypt it. She's going to keep that secret key secret and is able to obtain the original message that Bob sent. So the question here is this public key encryption even possible? It's got some nice properties here because everyone in the world could just publish their own public key. Everyone could have it in a phone book or on a web directory, and so it's nice. And I can communicate with a stranger with, I can do it offline. I can prepare my message and send them the message. I don't need to have this interactive protocol. I don't need to ever do any key exchange with them. I just need their public key. But some problems there is, is this even possible? Before a certain time, it wasn't even known if you could do this. Another thing is, how do you actually get Alice's public key? And why do you trust that the ciphertext has not been modified? Just because you encrypt something doesn't mean that the ciphertext hasn't been messed with in transit. And the second question here is actually part of the exercise. Is you're going to do one thing where you're going to get my public key and use it to verify a message. And somebody's already done it before the class, actually. So yeah, the first question is, was this even possible? And in 77, RSA, which is Revest, Shamir, and Edelman, showed a scheme that could actually do this. But again, this is actually invented in the intelligence community in 1973. Clifford Cox had it was kind of a rudimentary version. It wasn't as generalized as RSA, but they knew about this years in advance, and I thought that's pretty interesting. But some of this is kind of discrete math, so I'm not going to go too much into it, but here the public key is just going to be this exponent and an n, and an n is a large composite. And to encrypt a message, I'm just going to raise that message to the exponent. And in this case, it was often 3 or like a Fermat prime, but it's kind of public value that everybody knows, and they're just going to take it and mod this group n, which is a large composite. And then to decrypt, I'm just going to raise it to another exponent, d. And so, again, you can read the paper that's linked online. It's pretty easy to read through because it's, again, one of the first papers in this area, and it's very interesting. Now, some problems with this is that the ciphertext is a fixed size. It's going to be as big as this group, and so you can't encrypt arbitrary size messages this way. Computation is still relatively expensive. Back in the 70s, it was very expensive, and even today, it's expensive. You need to do this over very large groups. And again, why do we actually trust that the ciphertext has not been modified? When I get this value C, somebody might have done something to this. And so, for example, I can multiply values in there and change the value that you're going to get that you're going to decrypt. So there's no notion of authentication here. And more technical thing, this is not what's called semantically secure, and I'll talk about that in the third lecture. But that has to do with this, with some of the properties of the crypto system. But now we've got a way to actually do public key cryptography. So I keep coming back to authentication. And what about, how do we know Alice is actually Alice when we talk to her? And how do we know that a message came from her? And how do we know that wasn't altered in transit? So if I get a message claiming to be from Alice in the previous message, how do I know it's actually from her? How do I know it hasn't been altered in transit by somebody else? So another cryptographic primitive that didn't really have an analog in the classical era is authentication primitives. And one of them is a message authentication code. And this is very similar to a cipher. So it's kind of similar to DES, AES, where Alice and Bob will share a secret key. And there'll be two functions, sign and verify. And basically, anybody who shares a secret key can sign a message and produce a signature. I'm using Sigma for that. And then if I give you the message and the signature, you can take that secret key and verify it. And so these are often constructed from other primitives. There's a lot of literature on MACs, and they're basically an analog of ciphers. And so what I could do is I could send you a message that's encrypted along with a signature on it, and you both know that the message hasn't been altered, and because you believe that I share a key with you, you know that somebody who shares a key with you actually produced that. So it doesn't really identify the person who sent it, but you know that whoever sent it shares a key with you. And again, this has the same key distribution problems as ciphers. If you want to be able to sign a message to anybody in the world, you need to create n square or n keys for everyone in the world. And it's exact same key distribution problems. So like with public key encryption, we could talk about public key signatures. So it's very close analog. And the idea here is that anybody in the world should be able to sign the message with a secret key this time, and that anybody in the world can verify it with a public key. And so this is what I've done. I actually sent a message out to the mailing list that's signed with my secret key, and anybody here can go grab my public key and verify that the message actually came from the person who knows the corresponding secret key. So, like a public key scheme, this is going to consist of 3 algorithms. One of them generates a verifying key and a secret key, or a signing key. And then Alice will now, rather than publish the public key, she'll publish the verifying key, so anybody in the world can verify. And to sign a message, it's the same type of operation. She'll take her secret key or signing key and apply it to the message and output a signature. And then Bob, I don't have the signature in there, but he can take a message and a verifying key and the signature, and it'll say, is this valid or not valid? And so this is a nice primitive that allows anybody, yes? You could do it, and I think there's 2 issues here. One is that it's just the complexity of it. I need to manage n keys instead of, actually, public key system, you would still be managing n keys yourself, but you'd need to create and distribute n keys. So it takes away one side of it where we each create 1 key and need to store n keys for our friends. So kind of rather than having to, everybody has to store, well, I guess everyone does have to store n keys. So it makes it easier to create your own key and manage your own secret key. So instead of having to manage n secret keys, I need to manage 1. Yes? I'm going to talk a little bit about that. Yeah, so I'm going to talk a little bit about PKI in a minute, and about how do we actually trust these public keys. Yeah. So yeah, what he was saying was that if you want to do a key online, or if you want to establish a key with like Diffie-Hellman, both parties would have to be present and online. And using a public key scheme, I can prepare this offline and do it at home, and then when I log on, I can upload my messages and send them to you. So, okay. So, yeah, so basically public key signatures are kind of an analogy of a Mac, and it kind of brings up the same questions. Is this even possible? I mean, can I do something like this? And this was a question, early on. When people kind of proposed these ideas, it wasn't clear whether it was even possible. And again, we have this distribution problem. How do I get my verification key out there? Why do you believe it? And it turns out that this is possible. And RSA can actually also be used as a signature scheme. And that's a very nice property of this crypto system, and is why that it's gotten so much usage and so much attention. It actually won a Turing Award for the creators because it's both can encrypt and sign data. But it's only fixed size. So I can only sign messages that are so big. And how do I actually sign big messages? So this leads into the next primitive I'm going to talk about briefly, which are message digests. And there's kind of a lot of overlap with message digests and hash functions, and a lot of kind of collisions in the naming, because there's hash functions out there for hash tables and like universal hash functions, which aren't security related. So I'm going to use the term message digest to kind of distinguish in that, but basically it can compress an arbitrary length input down to a fixed size output. And there's no keys involved. So right now there's standards out there, they're message digests. One of them is called SHA-1, secure hash algorithm, one version. And one that used to be used more was called MD5, which is now broken. But there's basically just algorithms out there that you can use. And typically in cryptography, they want to have 1 or 2 properties or both. And these 2 properties are actually, you can have one or the other or both together. It doesn't necessarily imply each other. And one of them is called one-wayness, and I'm kind of informally describing it. It basically means that if I give you the hash output of something, it's hard for you to invert it and find the preimage. And that's kind of often the way that people think about it. They're just like, it's a one-way function. The other one that's actually more important for signatures is collision resistance. That means that I've hashed to a value, and it's hard for somebody to find any other value that hashes to it. So I don't really care about inverting it, it's just finding a collision. And one of the homework or exercises is to see who can find who can find the biggest collision. So it's hard to actually find a full collision, but you can find collisions on the prefixes. And so we're gonna have a little like contest to see who can get the largest one. If you get up to the entire thing, that's a pretty huge breakthrough. But I put one up there that's like 32 bits out of 160, so that took like under a second. And so we'll see who can actually get the biggest one, and it's gonna go till next Wednesday. So basically the noon before the next lecture, we can see who get the biggest one. And so yeah, I posted that on the mailing list, and you can check that out. Right, so and the reason why message digests are useful is that I can take an arbitrary size message and hash it down to this thing that's difficult to find something else that collides to. And then instead of signing the whole message, I can just sign the small hash function. And this is nice because we can put together these primitives, and I can now sign arbitrary length messages. And so I'm relying on both the signature being hard to forge and the message digest being hard to find collisions. So we go back to key distribution, and it's still a pretty major problem. We have this issue of how do I get your public key? And so, I put my public key up somewhere for you to find, and it shouldn't be hard to find, but how do you actually believe that I did this? And when I was at MIT, we did this in the class as the same assignment, and what some students did, they went up and put my public key up for me, so they were getting the messages themselves, and there's no way to actually take the key down and let people know which was which, so it's a problem. And so one way that you can think of this, now that we've got these kind of primitives, we've got public key signatures, we have public key encryption, we have message digests, a tool that was actually invented by Lawrence Kohnberger's at Google now is called a certificate. And what a certificate is just a signature on a public key. So I could put up my key on a web page, and then somebody else can sign it and attest to it. And if you go in your browser, well, you can look at it in your browser. There's a bunch of certificates, and these are signed by what are called trusted authorities or roots, and they're just people like VeriSign and AT&T and all these companies who their business is basically signing certificates, signing people's public keys. And what you end up getting is like a graph. And so you've got these trusted roots at the top, and then they confer trust with a signature, and they sign other people's keys. And those people can sign other people's keys with their keys. And you end up with these chains of certificates. And so when I send you a message that's from me, and I say, hey, here's my public key, what you can do is go look up and say, okay, well, his public key is signed by Google, and Google's key is also signed by them. And I can get a bunch of signatures on my key, and that's kind of an attestation that it's a valid key, that is my key. And so some people like VeriSign, you actually have to go in and show them an ID or something, and it kind of depends, but that can give you an idea of why you would trust somebody's key. And so one kind of in the early 90s, there was this software called PGP, which is now, there's a new one called GPG that you're going to use for the first exercise. And its model is a little bit different. And rather than have one trusted authority, it's kind of like more of a social graph. It's like a web of trust. So you would actually just sign the keys of your friends, and they would sign yours. And your friends would sign their friends, and you'd end up with a chain coming from different directions. So if I wanted to communicate with a stranger, we are likely to have maybe some friend in common who signed us both, or he knows somebody, and you basically could find a path from your friend to another. So there's kind of a nice analogy with all the social networks now. It's like all those connections could be public key, they could be certificates, they could be signatures from one person on somebody else's key saying, yeah, this is so-and-so, and this is their key. But there's still some problems out there of how do I actually revoke a key? If I get my laptop broken into and my secret key stolen, how do I go tell the world that my public key is no longer valid? And one thing here that you may hear about is called certificate revocation lists. These are basically just revocations that are pushed out there. But basically, PKI is still a very hard problem, and actually getting the keys out there is very difficult. So that's pretty much all the material I have for today. And like I said, the rest of the course next week is going to be more kind of practical engineering, like how to use crypto in your code. Third week is going to be more theoretical and the math side, and talking about security definitions. And the last week will be whatever topic people are most interested in, and you can vote on the QDB page. I'm going to go look at the see if anyone's put stuff on QDB. And please repeat any questions you have for the benefit of the audience and the VC. Sorry about that. Yeah, pretty much. I'm going to probably answer these offline. These look a little bit more geared for next week. But if there are more questions from the audience, feel free to ask right now. Yes? Could I give my PGP fingerprint? I will send it. I will send it out to the mailing list. I don't have it available right now on the screen, but that would have been a good idea. How about this? I'll put it on the wiki page because I've got the. No, okay, don't trust it. You can come to my desk and I'll get it to you, and I'll show you my ID. Yes.
It would seem that for message digest algorithms that if you fail the one-wayness test, you implicitly fail the collision resistance as well.
It's not necessarily the case, actually, and this is kind of an exercise that you can do. Is you can construct, a hypothetical one-way hash function that is not collision resistant. Usually, it's kind of something stupid where you make it easy to collide on purpose. And so these are two separate properties, and they are. Yeah.
My implication was though that if you have something that fails the one-wayness test,
Right.
you can always just generate the key randomly and then generate another one that collides with it. If it fails the one-wayness test, unless it only fails the one-way test for very special cases.
I have to think about that. I think that, these are separate properties. There's actually three different properties, and one's called pre-image resistance, second pre-image resistance, and then collision resistance. Collision resistance is actually two of the three. One-wayness is two of the three. And I hear what you're saying, but I have to think about it offline. Yeah. Yes?
Question that's more socially oriented. Why is it so, this is from my experience, why is it so hard to get people to understand the value of using crypto and email and so forth? And why are they so reluctant to do so?
So I think this is kind of a lesson from the first exercise, is that actually using this stuff is hard. And like even setting up that first message took me a while. And then the first person to respond took them a half an hour. I think the average MIT grad student in the security course, it took like 90 minutes to just decrypt a message and then send us an encrypted message. So I think, I don't know if I repeated the question. So the question was, why do people not use crypto in practice? Why is it hard to actually get people to use this? I think usability is a huge part of it. And, almost every email client out there, like Outlook, has S/MIME compatibility, and it has for years. So there's no reason why people couldn't start using this today. And I think it's kind of a usability and just actually having the infrastructure there. It pretty much needs to be invisible for it to be universal. Like there's no way people are going to take the extra step to encrypt their mail unless it's a very special case.
So the two-time pad examples, is that base 27?
Two-time pad examples are, yes, base 27. So it's the alphabet in space. Yeah. And I can post some Python code to do it if anyone needs that. Yeah. All right, is there any more questions? All right, well, thank you very much, and I'll see you next week for more practical use of cryptography.